So I'm going to give a series of lectures about the use of Coq for verifying the correctness of functional programs. And there are many interesting algorithms that work well in a pure functional setting. And when we verify pure functional programs, it's particularly elegant and simple because we don't have to reason about transformations on program state. We can just do direct induction on the values passed as parameters to functions in recursive calls. So if we want to do large-scale software engineering, there are many parts of the software that we can write as functional programs and verify them directly, and reserve imperative programming for the place where we need the particular kinds of performance and latency guarantees that imperative programming can give us, but then the verification of imperative programs uses a more difficult proof theory. So we want to stay in the pure functional place where we can, and we can verify those programs. So this textbook, volume 3 of the Software Foundation series, is Verified Functional Algorithms. And it covers insertion sort, selection sort. Now, when reasoning about the correctness of sort algorithms, you need ways to reason about ordering, total orders, and comparisons. And depending on how you specify the correctness of your sort algorithm, you might need to reason about permutations. So this early chapter just covers basic techniques for reasoning about permutations. Another way to specify sorting algorithms is not by permutations, but by multisets. So there's a chapter showing how to reason with multisets. In the lectures, I'll use the method of permutations. After some simple sorting algorithms, we come to binary search trees, which is one of the most important data structures for pure functional programming, because we need finite maps from a totally ordered key to some value type. And in imperative programming, when the totally ordered key happens to be a contiguous range of the integers, we can use arrays with array update. But we don't really have arrays with efficient update in most functional programming languages. So binary search trees become even more important. When we reason about algorithms, well, an algorithm is there to implement a certain abstraction. So data abstraction is very important in reasoning about algorithms. And so I'll explain how abstract data types work in program verification using binary search trees as the example. When we write functional programs in Galena, in Coq, and we execute them in Coq, we can execute them by beta reduction or by other methods inside Coq that are a little faster. But sometimes when we write algorithms that are meant to be efficient, we would like them to run faster than they do in Coq. So one of the nice things about Coq is that you can extract functional programs from the Galena language into ML or Haskell, and then you can compile them with your ML or Haskell compiler and integrate them with other software that you write that maybe you didn't prove correct. The extraction chapter of this textbook shows, how to extract the binary search tree program and run it on some test cases in ML. Well, binary search trees are very nice. They have log n time for insert or for lookup, if you're lucky, if they stay reasonably well balanced. But binary search trees can become unbalanced, and for better guaranteed worst case asymptotic efficiency, you want balanced binary search trees. So I'll show an implementation of red-black trees with a verification of their correctness and the verification of the bounded height of the trees as a function of log n, the number of elements in the trees. When you want to have lookup tables where the keys are integers in Cox's standard binary representation for integers, the Z type, there's something you can do that's more efficient than binary search trees. You can do binary tries, which are trees that index at each level of successive bits of the integer. So I won't cover binary tries in these lectures, but it's an important data structure for programming in Coq, and I encourage you to read that chapter. The next two chapters deal with priority queues, and in particular binomial queues. And I probably won't lecture about binomial queues, but it's a beautiful data structure. It's priority queues with log n time for insert, log n time for delete min, and log n time for the union of two priority queues. And it can be easily implemented as a pure functional program, and the verification is elegant and great fun. Okay, so today I will cover sorting, a couple of simple quadratic time sorting algorithms, insertion sort and selection sort. One might think that quadratic time sorting algorithms should never be used. You should use quicksort or merge sort or something. But actually, insertion sort is quite efficient on reasonable size inputs. It's easy to implement. It's easy to verify. And the verification of insertion sort will be your homework. And I strongly encourage you to do that homework. It's not that difficult, and you learn the principles of reasoning by induction about recursive functions. So here's the insertion sort program. The way insertion sort works is that you maintain some sublist of the elements that is sorted, and then each new element in turn, you walk through that sublist to find the right place for it to go, and you insert it in that place. So each pass through the sublist takes at most linear time in the length of that sublist until you find the right place to put it. And then there are n passes. So it's a worst case n squared algorithm. If the list is already sorted, then it may be a linear time algorithm as the amount you have to move each element to get it into the right place is, 0. And it's easy to implement as a pure functional program. If you look in the textbooks about insertion sort, they do it in arrays. And you might think, oh, these sorting algorithms can only be used in arrays. But it works beautifully on lists in a functional program, as you can see. To sort the list L, well, the empty list is already sorted. And to sort the list H cons T, well, sort the tail of the list recursively and then insert H in that list. That's easy. And here's the insert function. To insert element I in a list L, well, if list L is nil, just cons I on the front. If I is less than or equal to the head of the list, then put I on the front. Otherwise, insert I in the tail of the list and then cons H onto the front. So easy. Easy to write, easy to run, easy to verify, and you'll have time this afternoon to verify this program. Okay, so let's look at what does it mean that a sorting algorithm is correct? Well, you take some input, you get some output, and the output has to be in increasing order, or at least monotonically non-decreasing order. The output has to be sorted. All right? Is that the specification of a sorting algorithm? Well, not quite, because any program that takes an arbitrary list and returns the empty list would satisfy that specification. What we'd like is that the output has the same elements in it as the input also, so that the output is a permutation of the input, or that the output is the same multi-set of values as the input. So either way of specifying that works, and we'll do permutations. So therefore, we need a theory for reasoning about permutations. And let's look at that theory. So, we're going to import and then re-export the Coq permutation library from the standard library. Before we get to permutations, though, I want to talk about comparisons. The other thing that sorting algorithms do is comparisons. In these chapters, we will use the natural numbers. So we'll have sorting algorithms on lists of natural numbers. The natural numbers are not really a great data structure for computation, right? The natural number n has a representation of size n, and to compare whether 1 million is greater than 1,000,001 takes time proportional to 1 million. This is terrible, right? And in fact, the Coq Z type for the integers is a much more efficient data structure. It is really a binary representation, arbitrary precision binary. But for these exercises, we'll use NAT. We'll ignore the fact that comparisons of natural numbers take a long time, and we'll just worry about how many comparisons we have. And all of our sorting algorithms will generalize nicely to any other data structure, any other representation of numbers that might have more efficient comparison operators. So let's use the Coq check command to learn some things about various operations on natural numbers. Nat.lt is a relation on natural numbers. So it's a proposition. It says, one number is less than another. LT is the same as nat.lt just because of the way we have imported the nat module so that we can see it visibly. All right, so I claim that nat.lt equals LT, and it's proved by reflexivity. So it's the same thing. All right, now, LTB is nat arrow bool. So this is a computable function that you give it two natural numbers, and it returns true or false. We can compute with this one. We can't compute with nat.lt. Right? Propositions are not the same as decision procedures. If they were, we could sort of all go home and not have to verify anything anymore because mathematics would be easy. Now, so nat.lt is what we're going to use to specify the correctness of sorting algorithms, but nat.ltb is what we're going to use to implement sorting algorithms. What's next? This notation, if you're not sure what a piece of notation means, you can use the locate command. You can say locate, and if it's a notation that you want to locate, you put it in double quotes like that. And when you're a new user of Coq and you're not sure where these things come from, this locate command is extremely useful. When you're an extremely experienced user of Coq and where you're not sure where these locations come from, the locate command is extremely useful. Okay, but I don't want all of these notations. I just want the notations of the form blank less than blank. So I'll put that in the locate command. And it says, well, in different notation scopes, less than can mean different things. So we should just be aware that notations are overloaded. Depending on what we have open, which appears to be nat scope, because that's what the default interpretation means, I think, it'll be the natural number less than. Now, there's this other notation, less than question mark, and we can see that it stands for the Boolean less than test, the computation. So in our proofs, we're going to be relating less than to less than question mark. And indeed, here's a theorem, nat.ltb underscore lt, that says n less than question mark m is true if and only if n is actually less than m. So that's the kind of theorem we might use to relate things. Okay, we might want to reason about greater than or equal. The greater than or equal operator is notation defined in the Calc library, but for some reason, greater equal question mark is not in there. So let's add it. Here's the notation command that would bind nat.leb to the greater equal question mark notation, and the same for greater question mark and equal question mark. Okay, but to do proofs that relate LT to LTB, I find it convenient to use the reflect type. So, as you've seen in a previous lecture, reflect relates a proposition to a Boolean. If the proposition is capital T true, it relates to the Boolean lowercase t true, and if the negation of the proposition is capital T true, it relates to the Boolean false. Let me unsay my last sentence and say it a different way. It's not that the proposition P is capital T true. There are many valid propositions that hold, other than just capital T true. For example, 5 greater than 3 is not the proposition true, but it's still valid. So if P is valid, it relates to the Boolean true, and if the negation of P is valid, then reflect relates it to the Boolean false. Okay, and here's a simple theorem, BEQ reflect, which says that for all x and y, the formula, the proposition x equals y, relates to the Boolean value you get by computing x equal question y. And so we prove that theorem by some lemmas that we had lying around. We can make a reflect lemma for BLT reflect, relating x less than y to x less than question mark y, and same for BLE reflect. Now let's use these reflection lemmas. We want to prove this, that this value on the left, which is if a less than question 5, then a else 2. So compute the Boolean LTB A5, and if it's lowercase t true, then return a, else return true, and that whole thing is going to be less than 6. That's our claim, and I'm going to do destruct BLT reflect A5. So what is BLT reflect? Let's do check. That has the type reflect a less than 5 relates to a less than question mark 5. And as you remember, reflect IJ is an inductive proposition. So if you destruct it, it will have 2 cases. And each of the cases carries along a proof in it, a thing of type P or not P, because that's the type of the first argument to reflect, is a thing of type P, a proof of P. So when we destruct BLT reflect A5, we'll call it in either case H, the new thing that gets introduced. And here, the thing of type P, H has type A less than 5, meaning A is a proof of A less than 5. And now, how do we prove that if A is less than 5, then A is less than 6? Well, we used the theory of linear integer arithmetic. We used the omega tactic. Okay, that was easy. In the other case, we have a proof of not A less than 5, and we have to prove 2 is less than 6. How do we prove that 2 is less than 6? The theory of linear integer arithmetic, of course. Beats thinking. Okay.